Welcome to this video on angular momentum part 2. We're going to pick up where we left off in the last video, and in the last video, if you haven't checked that out, you want to go back and look at that, because we developed the idea that angular momentum, which is symbolized with uppercase L, is equal to the linear momentum cross the radius vector, or the position vector of the object. That we expanded to be mv cross r, which we could also show as mv sine theta. In addition, we showed that the rate of change of the linear momentum, so if you change something's the rate of change of angular momentum, if we change an object's angular momentum, the speed at which we do that would determine how much net torque was acting on the object in order to change its rotational motion. Now what we're going to do in this video is take a look at an alternative way to understand angular momentum, and we're going to do that by doing some substitutions. So I'm going to go to this perspective, mv cross r. Okay. In fact, I'm going to remove the cross product for this video just for simplicity here. And we're going to establish the fact that v is equal to omega times r. This is going to allow us to take angular momentum and put it not in terms of linear velocity, but in terms of angular velocity. So I'm going to go ahead and do the substitution. So I have m times omega times r times r. That leaves me with m times omega times r squared. With a little bit of rearranging here, I'm going to see that I have mr squared times omega. Now, if you think back to the idea for the moment of inertia, or the rotational inertia, so that's the resistance to rotate. So the rotational inertia for a point mass, the equation for that was mr squared. So we see here that we've developed a new perspective for angular momentum, which is L is equal to I times omega. So we can see here that you can calculate the angular momentum of an object by knowing its rotational resistance, or its rotational inertia, and its angular speed. Now this is a very interesting perspective. So what we can do here is, as we said at the end of the last video, that for a planetary orbit, so in a closed system, planetary system that's closed, that means that there are no changes in force that are happening to any object that's asymmetrical to the other objects. We can say that the momentum at any time, so we can say the initial momentum is equal to the momentum at any other time. That means that we have something that looks like this, where we have the initial moment of inertia times the initial angular velocity equals the same values at any other time. Now you might be thinking, well, the angular momentum can't really change, or the rotational motion can't really change, or the rotational inertia can't really change unless something causes that change to happen. And that is true. So let's go ahead again and take a look at our orbital path with the sun here at one focus, and we can put the Earth at different places. So let's go ahead and compare the further away point with the closer point. Now we know when the planet is closer to the point around which it's rotating, that it's going to be moving faster. But let's look at it from a different perspective. The moment of inertia, or the rotational inertia, is less over here. So if we think of rotational inertia from all the other videos we've looked at so far on that topic, we know that if the mass is closer to the axis of rotation, you have less resistance to change. So over here, we know that L, let's call this L sub c, is equal to I sub c times omega sub c. Now we know that the angular rotational inertia has dropped a little bit, and because we've seen that the angular momentum is staying constant, that means that the angular speed has increased, which is what we found in the previous video. Now if we look at when it's further away, where we could put L sub f is equal to I sub f times angular speed times f, we see that when the mass is distributed at a further away distance, the moment of inertia is higher. And when this is higher, with a constant amount of angular momentum, the speed will be less, the angular speed will be less. So both of these equations, mv cross r and I omega, are really saying the same thing from a slightly different perspective. That actually allows us to analyze some very interesting situations that we see in a lot of very cool examples. So let's take a look at two of those. The first has to do with a figure skater. So let's take a look here. I'm going to draw my very humble sketch of a figure skater with their arms spread out. Okay, let's say that they're spinning around in a circle. So we'll draw this to represent the fact that they're spinning. Now, when they start to spin, they've pushed with a certain amount of force, which would provide them a certain amount of torque, which would change their rotational momentum. Now what's going to happen is, as this figure skater spins, they're actually going to pull their arms in closer to themselves. And what that's going to do from the perspective of this equation is that here, let's call this I initial and this I final, we've seen that what's happened from here to here is that the I initial, or the initial rotational inertia or moment of inertia, was larger because we had the mass of the person's arm spread out a lot further. So it's going to be less over here or more over here than it is over here, which is I final. So if we look at the speed then, knowing that the angular momentum is conserved within a system where there's no external forces acting, we see that the speed initially would have to be less than the speed is now at the final position because of the change in rotational inertia. That's kind of cool because that means that as you turn, as you pull your arms in, you should start to speed up. You can do this for yourself. If you sit on a swivel office chair and you spin yourself around, starting with your hands open, if you pull your hands in towards yourself, your speed will actually increase. The opposite will happen if you push your arms outwards, you'll slow down. So this is just another application of how angular momentum can be conserved in a system, and we can change the speed when we change the moment of inertia. Another way that we can change the moment of inertia would be to either add or subtract mass from the system. So if you think of a disk, this would be a solid disk spinning around somehow. It's on an axle of some kind. And if I drop another disk on top of that onto that same axle while it's spinning, what we've done is increased the rotational inertia by increasing the mass instead of by changing the distribution of the mass. And because of that, the moment of inertia will go up and the angular speed will thus go down. Which makes sense because if we have a finite amount of rotational exertion here to change the momentum, changing any of these things will end up changing the mass. This allows us to solve for many different things in different substitutions, and also how a lot of mechanical devices work can be by changing the moment of inertia of the device and therefore changing its speed.